Okay, so this will be the first recording for the week. I might have to be doing some of this from home, depending on what happens. My original plan, the devices I had, I could not get a very good video quality, and so I'm going to voice over the lectures. I'm also going to try to insert some drawings that I would have done on the board at various points in the slides as I work through them. I don't think that'll be too necessary for what I'm doing today. With a lot of the pictures I have in the slides, I'll use my cursor like I would on the board. I'll also upload an Excel help file. So for confidence intervals, which is the subject for this week, I'm going to walk through like a little tutorial just like I have for other Excel assignments like we do one in class. Then you can follow it as a good template. So I'll upload that as well. That being said, hope all of you are safe and healthy. And here we go. So, we kind of stopped last class talking about the distribution of sample means and sample proportions. So we said as long as that central limit theorem is met, we've got a sample size over 30, we can know that our sample means and our sample proportions would be normally distributed. Now the whole point of taking a sample is we hopefully eventually want to try to pinpoint down where the population parameter is. So whether or not that's the population mean or the population proportion, that's what we're using our sample to do. So 99% of the time, we're not going to know what that population mean or proportion is. So we're going to use our sample values to predict it. And why we care about, well, we care about making predictions because we want to know where those true parameters lie so we can make policy decisions, right? So how can we do that? Well, if we can limit the bias, like we talked about with all the random sampling, stratified sampling, eliminate some of those non-response biases, but we also, if we can get the variance on our sample mean distribution to be really, really low, well then it's very likely that we only see values around the mean. Remember, if we have a smaller variance, that gives us like a more peaked or a higher, kind of taller looking distribution. And so the values right around the mean would be way more likely, right? It's more peaked. That represents the probability of seeing those values near the mean are going to be much more likely. So we want to try to get a small variance. So the general idea of what we're going to be doing with confidence intervals is we don't know where the true population mean or proportion lies. So we want to try to get a range of values where we can say with 90% or 99% confidence, I can tell you based off of the sample data I have that the true population mean or proportion is somewhere within this range, right? So we'll take a sample. From that sample, we're going to try to estimate this where the true population lies, and we're going to try to pinpoint this down in between a lower and an upper bound. Okay. So the example kind of that I'll run off with, we look at this birth weight data, and so we don't have every single birth weight sometimes. Even the data set I showed you was just Indiana births, so maybe we want to know about the whole United States birth weights. And so we're going to take a sample, and we can get a sample mean birth weight. Right? Based off that birth weight, we're going to use that and say this is the best estimate that we have. But look, we know that even if the true mean birth weight was, let's say, 3,500 grams, it is very likely we could see 3,450, right? That's not very far away from that sample mean. And so even with a relatively low variance, we may still see values to the left, to the right of the mean. Now, it'd be very unlikely that if the true population mean was 3,500 or 3,500, that we see a sample mean of 1,000, right? That's very far away. It's very unlikely we'd see that. And so we're going to use our sample mean as like the best guess for where we start, right? So that's our starting point. And then from that, we're going to go above and below that sample mean to figure out, okay, what lower and upper bound can I create that I then say my population mean has to fall within this range with a certain level of confidence. Okay, so I kind of already mentioned this, but with 95%, 99, 90%, we can choose whatever level of confidence we want. Right? So the general idea is we'll take that sample mean because it's our best guess of where that true population mean lies. All right, so we'll take that sample mean. To get the lower bound, we'll take the sample mean and subtract some amount. And to get the upper bound, we'll take that sample mean and add to it that same amount. Now, it's not maybe the most perfectly correct nomenclature to do this for sample means and sample proportions, but I'm going to call this guy here W. We're eventually going to call that's our margin of error. We're going to add and subtract a margin of error to our sample mean, and when we subtract it, that gives us the lower bound. When we add it, it gives us the upper bound. Okay. So then the next question is, how do we choose this W, right? How do we figure out what this margin of error is? So if we think about the distribution of our sample means, okay, we're thinking about that, we know that as long as that central limit theorem is met, we'll have a normal distribution for them. Okay? So let's say we want to build a 95% confidence interval. Okay? From what we've looked at before, anytime we go 1.96 standard deviations away, and right, that's just a z-score of 1.96. If we want to think about the area to the left of 1.96, negative 1.96, it's 0.025. If you think about the area to the right of positive 1.96, it's also 0.025. Right, this was a symmetric distribution, it was a normal distribution, so we knew that if we were looking the same number of standard deviations above or below, that the areas more extreme than those, right, or the areas to the right of the positive z-score and the area to the left of the negative z-score would be the exact same. So if we think about using this value of 1.96, going 1.96 standard deviations away, so whatever the standard deviation is, multiplied by 1.96, if we added that and subtracted that to the sample mean we found, the area in between those two values would be 0.95, right? Because the area outside would be 0.025 on one side, 0.025 on the other. So the area within those two bounds would be 0.95. Okay? So we think about the area not in the tails would be 0.95. So the area in between 1.96 standard deviations above and below, the area in between those would be 0.95. The area outside, right, when we add these up, will be 0.05. Okay? We'll think about it visually. If I took whatever the true mean, if I could see it was, and I went 1.96 standard deviations below and 1.96 standard deviations above that true mean, I know that the probability I see a sample mean somewhere in this range would be 0.95, because the probability I see something further than 1.96 standard deviations below is 0.025. The probability I see something 1.96 standard deviations above or more, that area or probability is 0.025, and so the probability I see something in between those would be 1 minus those two areas. 1 minus 0.025 minus 0.025 is 0.95. Okay? So we can think about the confidence level we want is like the area that we want not in the tails or in our confidence interval. Right? So 95%, we want the probability that we see something in within our confidence interval would be 0.95. The probability we see something outside of that would be the remainder, right? If 0.95 is within, 0.05 is outside. Okay? So, I kind of give a nice visual as to what we're doing with confidence intervals in order to, kind of relate that to also to this 95, 99%. So let's say we don't have the population mean, right? We wish we did. We wish we could do this. All we have is our sample mean. But let's say I could observe where that true population mean was. If I take a sample and I find the sample mean to be right here, right? It's just a little bit below the population mean. And I then construct a confidence interval around that, right? I go 1.96 standard deviations above and below that sample mean. I treat it as though it is the population mean. So I treat it as though it is the population mean. I go 1.96 standard deviations above and below in order to get an area of 95% or 0.95, or the probability that I see values in between here is 0.95. Right. Then notice this confidence interval includes the true population mean. So if I would then take another sample, okay, maybe I see a value that was a little bit less likely, right, further from that true population mean. But if I build a confidence interval, right, create the lower and upper bound around that sample mean, treat it like it is the population mean, notice, well, that range of values also includes the population mean. If I did this for any value within this blue area, if I see any sample mean in this area, and I then build a lower and upper bound construct a confidence interval around it, it will always include that population mean. The only sample means I could see where my confidence interval doesn't include the population mean is if I see something more than 1.96 standard deviations below or something more than 1.96 standard deviations above whatever that true mean is. But I know that's a relatively low probability, right? I know the probability I see a sample mean that's further than 1.96 standard deviations above or below is only 0.05, right? I know the probability that I see something that's at least 1.96 standard deviations I know that the probability that I see something that's less than 1.96 standard deviations above or below this true mean, I know that probability is 0.95. Okay? So, right, I know that 5% of the time here I'd be constructing a confidence interval that didn't include the population mean, but 95% of the times for all these possible sample means I could see in this blue area, 95% of the time it would include that true population mean. So that's why I can say with 95% confidence, if I base my confidence interval off of the sample mean I saw, well, with 95% certainty, 95% of the time, that confidence interval would include the population mean. And yeah, I'd be wrong 5% of the time, but that's why I can't say it with 100% confidence, right? So this is a general idea of what we're trying to do with the confidence intervals. So the next thing that we're going to think about is if I have these different levels of confidence, I'm also going to have to denote what level of confidence that I'm choosing. And we kind of think about alpha is going to be perfectly related to whatever that confidence level is. So alpha is going to be essentially follows this rule: 100 times 1 minus alpha would be whatever. That would be the percent confidence we want to say it with. The way I say it, it's not perfectly correct. And, I mean, you wouldn't probably want to talk about this with a statistician, but alpha is the area outside your confidence interval, right, or the percent outside the confidence interval, but decimal form, right? So if I've got the 99% confidence level, well, then alpha would be, well, what's outside of my confidence interval there will just be 1%, and then in decimal form, 0.01, right? And that's really all this is saying, okay? So 0.01 alpha would be for 99%, 0.05, 95, and 0.1, 90% level, right? If I have 90% confidence, the probability that I'm capturing the true population mean is 0.9, right? Or there's a 10% chance that I'm not capturing it, and 10% in decimal form would be 0.1. Right? So that's how we get alpha from whatever level of confidence that we want. Okay? And we'll basically be using these three benchmark values. You could look at a confidence interval or a confidence level of 92%, but it's kind of weird to say, yeah, with 92% confidence I can say this. Like usually we just choose these benchmarks of 90, 95, and 99. Okay? We could also work in either direction, right? So I've kind of explained things in terms of if I say the confidence level is 99%, that's an alpha of 0.01, or if I have an alpha of 0.01, that's a confidence level of 99%. We're just working in two different directions there. So how we choose that W, that process I just described to you, well, I chose 1.96, if we go back. I chose 1.96 because I know that if my sample means are normally distributed, that if I want that area of 0.95 or 95% confidence, that the z-value that would give me that is 1.96. Well, how did I know that? Well, I could look it up in the table. Right? I could look up negative 1.96 in the table and find, oh, the area to the left of it, right, is 0.025, which means that if I looked 1.96 standard deviations above, the area to the right of that was 0.025. And so the only area that's left in between those two would be 1 minus both of them, or 1 minus 0.025 minus 0.025, which would be that 0.95 that I wanted. Okay? So what I did there was I knew the alpha I wanted, right? If I wanted the 95% confidence interval, I wanted an alpha of 0.05. That's what would be outside the confidence interval, but in decimal form. But I then knew I had two tails. So half of alpha is each tail. So 0.05 divided by 2 is 0.025. So that's the area that was in each tail, or the probability that I saw something that many standard deviations away. If I know the probability, and I want to know what z-score, how many standard deviations away I need to be to have that probability, well, that's just kind of doing the inverse that we talked about. I know the area I want in the tail, and I want to find the z-score that gives that to me. So I want alpha over 2 in the tail. I'll look that up in the middle of my z-score table, right? Because that's a probability. Once I find that probability, so I look up 0.025, I then go over and up to find the z-score that would give that to me, and sure enough, I'll find it's negative 1.96. Now, I always can look up alpha over 2 in the table, and then I just remember I don't really need that negative sign. That's already built into my confidence interval equation, right? So if I go back and think about, I wanted to go 1.96 standard deviations below and above, well, that I'm looking up this area, right? I'm looking up alpha over 2, so I'm always going to find the negative one. But I want to find the lower and upper bound, and so in order to get the upper bound, I have to add that. Right? Go that many standard deviations above the sample mean I saw. So this is take the sample mean that you found, subtract that z-score you just looked up of 1.96 times whatever the standard deviations of your sample means. Right? Go 1.96 standard deviations above that sample mean, and that would give you your upper bound. If you went 1.96 standard deviations below, and you subtracted, that would give you your lower bound. So this is our W that we were trying to find, and it was just going to be a number of standard deviations above and below the sample mean that we found from our sample. Right, so we should hopefully recognize all this, but what's the standard deviation of my sample means? We talked about, there's an equation for that, which would be taking the square root of the original variance of the data divided by the sample size. Right, so I'm going to have that right here. Right, it's on a different slide, but right, if I want the standard deviation of my sample means, we said that was just the square root of the population variance divided by the sample size. Okay? All right, now I'll go back here. So what are things that would change our confidence interval? Well, I think the easiest one, and I'll show you one in a second, but if we have a larger alpha, right, that's just going to mean that we're choosing a lower level of confidence. Because if we said, I want the 90% confidence level, well, that's an alpha of 0.1. 99% confidence level would be an alpha of 0.01. So if I want to say something with a lower level of confidence, then my confidence interval would just have fewer values in it, right? It would be narrower. So this would be the idea, if I wanted to say something with 99% confidence, I could say that it was in between the value of 0 and 100. But maybe if I can only say it with 90%, I have to include fewer values. I would say, well, with 90% confidence, I could tell you it's in between 10 and 90. Right? Saying something, I can say something with 100% confidence. How? Right? Well, I just say it's in between negative infinity and infinity. Right? I can always say things with a higher level of confidence if I just make my interval wider. Right? And so that's what this is saying. If I want to say something with a lower, if I want to say something with a higher level of confidence, that actually is a lower alpha, and so that would make my interval larger. But here I'm saying if I want to say something with a lower level of confidence, that's a larger alpha value, and that would give me a smaller interval or smaller range of possible values that the population mean to be in between. I could also take a larger sample size, right? So why would the larger sample size, how would that impact the confidence interval? If I go back here and I think about my confidence interval equation, right? This is what we're going to call the margin of error. When I add and subtract that, the margin of error is deciding how wide my confidence interval is, right? The sample mean is where I start the middle of my confidence interval. But to get the upper and lower bound, right, I have this margin of error. That's going to decide how wide it is, right? How far away from that sample mean I'm adding and subtracting. Or, sorry, how large the value is that I'm adding and subtracting that sample mean. So the reason why, if we had a larger alpha, right, if I want a larger alpha, that means the area that I want in each tail would be larger, which would mean, how do I make this area larger? I would have to go a certain number of standard deviations not as far from the mean, right? I can't go quite as far. And so when I want to say something with a higher alpha, that's going to decrease the range of that confidence interval. If I want to say something with so that's how that alpha is kind of operating, right? Because it's going to impact the z-score. If I have a higher alpha value, it's a lower z-score, which means I'm adding and subtracting a smaller margin of error, which is going to narrow that confidence interval down. Now, because we know that the sample size is in this equation, right, we said here, to calculate that standard deviation of my sample means, if my sample size goes up, what happens to the whole fraction? Well, if the sample size or denominator gets larger, this would go down. So higher sample size lowers that standard deviation on my sample means. So if this is getting smaller, then I'm adding and subtracting a smaller amount and going a shorter level above and below. It's going to narrow that confidence interval as well. So larger sample sizes decreases my confidence interval or makes that interval smaller. And then the last thing would be, well, if I have a larger original population variance to begin with, that's just going to increase my standard deviation on the sample means, and then my confidence interval is going to be larger. Right? So the original variance is larger, and the standard deviation on my sample means will be larger. Then the value I'm adding, subtracting to that sample mean, right? This is going to get larger, so this would get larger. I'm going to have a wider confidence interval. So those are the three things that impact our confidence intervals. Okay? Now, we can choose our sample size, right? Now, remember what we're trying to do. We're trying to get ideally, I would want to be able to say with 99% confidence that a population mean is within a very small range of values, right? With 99% confidence, I want to be able to say it's in between, 0.2 and 0.3, right? Well, how can I do that? Well, if I jack up my sample size, I increase it a whole bunch, it's going to drive down that standard deviation of my sample mean. It's going to make it a narrower distribution. And so when I add and subtract that margin of error, and this is really, really small, then that's going to make my interval small. So I'm able to pinpoint down. I can say, look, in this very small range of values, this confidence interval I've created, this is where the population mean lies. Okay? Now, I can't do anything to impact the population variance. That is what it is. But I can also kind of create a smaller range of possible values if I want to say something with a lower level of confidence. But that doesn't really help me, right? Because I'm just getting a smaller range, but I'm not able to say it with a high level of confidence. So the one thing we would really impact, even if I want to say something with 99% confidence, and saying something with 99% confidence is actually a small alpha, right? 0.01. So that would make my interval wider. But if I want to keep that level of confidence at 99, if I increase the sample size a lot, I can compensate for that and still get a pretty narrow range of possible values. So what does this look like with actual numbers here? So I'll walk you through how we plug these in, calculate our lower and upper bound. So let's assume a hockey puck has a variance of 49 grams. Let's assume that the variance on hockey puck weights are 49, right? So the production process doesn't pour the moldings perfect every time, so there's some variation when we're weighing these things. So if we take a sample of 49 of them, right, and we find the sample mean weight is 7.5 grams, okay? So maybe this is like I'm producing massive amounts, and I want to pull off 49 off the production line and be like, am I hitting my targeted weight, right? Because if the NHL is ordering these from me or something, and they don't end up being exactly the official weight, then that's a problem, right? I want to make sure whatever I'm targeting with my production process, that my product is actually weighing that amount. So I've got this sample, right? I want to build a 99% confidence interval, and hopefully once I do that, one of the possible true population mean values would be whatever I was targeting, right? Like let's say I was targeting 8 grams, and I take this sample, I feel, it's only 7.5. But that's not that far from 8. Can I still say that with 99% confidence that the true population mean still could be 8 grams, which was what I was targeting? I don't know. We'll see. We got to build it, right? So, how do we solve this? Well, identify what we're given. We had the sample mean, sample size, the original population variance, which would be very unlikely we know this if we didn't know the population mean, but maybe we just know what the machinery produces, what the variation in the machinery is. And then whatever alpha level we want to build. Right? So I think here I said 99%. So if we have a 99% confidence level, our alpha would be, well, what would be outside of our confidence interval, 1% in decimal form, 0.01. Right? So The next thing we would have to do is use that alpha to look up the z-score we need. We know alpha is the area in both tails, so we have to divide it by 2, because 2 tails, we got half the area in each side. We'll then look up that z-score. We can then do an intermediate step where we find the standard deviation for the sample means by using the equation we know dictates that, and then just plug everything in. So here's our lower bound, upper bound equation, right? Upper bound we add the margin of error, lower bound we subtract it. So we identify the information we're given, 7.5 gram mean, 49 hockey pucks sampled, original variance on the production process of 49, and the alpha that I already mentioned was 0.01. So we'll go to the table. We know we want to look up 0.01 over 2. So we go to the middle of the table because we have the area in the tail, right? We have the probability. We want to find the z-score that gives us that area in the tail, or gives us the probability. So we look in the middle of the table. We then go up to find the z-score that would correspond to that area of 0.01 over 2, so 0.005. I look that up. I find, and I could look up 0.995 to find the positive value, or if I look up 0.005, I would find negative 2.58, right? And either way, it's fine, right? As long as I have that value, I need the absolute value to plug into my confidence interval equation. I do the intermediate step of calculating the standard deviation of my sample means. So I take the square root of the population variance over my sample size. Here, I made the numbers nice, so it works out to be 1. That's a matter of plugging everything in, right? So 7.5 was my sample mean. The z-score I found was 2.58, and I calculated the intermediate step of finding the standard deviation of my sample means, which was 1. Right? So if I do that, now I look at the lower and upper bound. If I actually put this in my calculator, it looks like it does include that targeted weight of 8 grams, right? So if I'm going to the NHL or something, I say, well, look, we know this batch is only 7.5, but we know that for all hockey pucks we're producing, that the true population mean could still be 8. Okay? All right, we'll work through another example, like looking at it slightly differently. Okay? So usually I would use this as an iClicker question, but obviously we're not in person, so we can't do that. So let's say we're going back to that birth weight data. Right? We know that just from historical data, the population variance is about 9 weeks. Right? We take a sample of 81 births. We see that, no, this is not 9. Oh, sorry. This is 9. We take a sample of 81. We find a sample mean of 38 weeks. Okay? So we got a population variance. We find our sample mean. If I want to know where the true population mean is, or the true average length of a pregnancy, I want to build a confidence interval where I could say the true average is somewhere in this range. Okay? And I want to build it and be able to say that with 95% confidence. Okay? So we look at all these, options. If we think about it, one thing that we can always do to check to make sure things make sense is our sample mean should be smack dab in the middle of our confidence interval. If we're adding and subtracting the same amount to that sample mean to get the lower and the upper bound, well then it has to be exactly in the middle. Now I don't think you can rule out any of these. Looks like 38's right in the middle of all of them, so I didn't make it easy. But that's one thing we can do to check. Okay? So what information was I given? That's step 1. Well, I've got my sample mean, my sample size, my population variance, and at the 95% confidence level, right, if we go back, 95% confidence level, the area outside of that would be 5%, in decimal form 0.05. Okay? So I need to look up 0.05 divided by 2. Okay, so 0.05 over 2 is 0.025. Well, we actually looked that up earlier. So we have the area that we want. We go to the table, look up the probability in the middle, so 0.025. Go over and up to find the z-score that would give that to us. It's 1.96. Right, we looked up that up earlier. I then can do the intermediate calculation of calculating the standard deviation of my sample means. Right? So I plug in that population variance, plug in my sample size, I get that to be 1/3. Now I plug everything in here. Now notice, I wrote this in here because you could, instead of doing the intermediate calculation and like plugging that in, so if we go back to the previous one, Notice here I wrote it as the standard deviation of my sample mean. So when I calculated that, I could just plug it in. But if we didn't do the intermediate calculation first, and I plugged the actual values in here, so instead of plugging that in, I actually plugged, had been plugging this in, right, where I put in the square root of my population variance would give me the standard deviation. So plug a 3 in here, plug in the square root of 81, I'd still get a third. Right? So I can do the intermediate calculation, or I can just plug this right in here. Okay? Remember when I showed you the original equation, if I go back here, I apologize if this is a, here we go, right? This guy here, we said we knew was just this. So I could plug that in either way. All right, just a little bit different mathematics writing. Okay, whoops, there we go. So I've got my confidence interval. So 99% confidence, I could say the true average length of a pregnancy is somewhere in between these two values. So we'll go one more example, right? Let's say I've got a sample size of 35, right? And it's of these 45-pound weight plates. I went over to the rec center because no one's there. I grabbed 35 of them. I said, well, hopefully the production process should be producing 45-pound weights. But I look at this sample and the sample mean was only 46.5 pounds. These are actually heavier, right? But I only took 35 of them, right? Anything that's produced, the production process isn't going to be perfect for every single item, right? So it could still be that the true mean weight of all plates produced by that company was 45 pounds. Let's assume we know the production process has a variance on its machinery of 25. I want to build a confidence interval to where I could say, okay, what with 90-something% confidence that the true population mean is somewhere within this range, and hopefully within that range, one of the true population mean values could be 45. So if I want to say something with the level of confidence that's an alpha of 0.1, right? Well, now I have to work backwards. So I don't have the level of confidence, but I have the alpha. So alpha is the area outside of my interval, so that's 0.1. So the area inside my interval, right, the area under that curve is 1, so the area inside my interval would be 1 minus that, so 1 minus 0.1, which would be 0.9. And if I think about the probability I see something in between two values is 0.9, that could also be set as 90%, right? So 90% confidence level here. Now if I look here, 46.5 is what I'm going to be basing my confidence interval around. I could see, is it in between, smack dab in the middle of these values? It looks like it's in the middle of here. Okay, 46.5 is only about 1 away from the lower bound, but it's almost 3 away from the upper bound. This can't be a correct confidence interval. Our sample mean should be smack dab in the middle. I look at the other two. This one looks like it checks out. This one, wait a minute, 46.5 isn't even in this interval, right? Remember, we're basing this confidence interval off of the sample mean that we saw, okay? Okay, so we want to just work through it though, right? We limited the options down, we eliminated B and D, so we know it's either A or C here. So we identify the 4 things we need: sample mean, sample size, population variance, and then we were given alpha here, so I didn't even have to convert it. I then say, okay, alpha is 0.1, so I divide it by 2, I want 0.05 in each tail. I have 2 tails, so 0.05, I looked that up in the table, I can look up 0.05 and find negative 1.65, or if I looked up 1 minus that, I would find positive 1.65. I can do this either way. I can just look up alpha over 2 and remember I don't need the negative sign, or I remember it's symmetric, so if I want the area to the left of negative 1.5 to be 0.05, then the area to the right of positive 1.65 would be 0.05, meaning the area to the left would be 0.95. Now it's a little bit hard to follow with me probably just saying that. We can think about this though. I'll attach maybe a drawing or a video in here to where you can kind of see exactly where that's coming from. But I can look it up in 2 dimensions, right? I then find my intermediate, have the intermediate step of calculate the standard deviation of my sample means. So I plug in my population variance sample size, I figure out what that is. and I plug in those three values that I have, right? Because I now have a z-score, I've got the standard deviation of my sample means, and I have my sample mean. Okay? So I construct it, and we have a problem, right? Here's my lower and upper bound. With 90% confidence, I actually can't say that the true population mean could be 45, right? And so if I'm looking at this company, I'm saying, you guys have a problem, right? You're not hitting that targeted goal based off the sample I took. Okay. So let me switch things up here a little bit. I'm going to go to skip that. I can just skip that slide. Okay. So just like for the sample mean, we can do the exact same thing with the sample proportion, right? If we want to know where a population proportion is, we had this from last Thursday. We knew that the mean of my sample proportions is the true population proportion. We know the standard deviation of my sample proportions would be this. Now the problem is, we don't know the population proportion, so what we're going to now do is, well, the best estimate we have of it is whatever sample proportion we found. Okay? So we can construct a confidence interval for the true population proportion based off of our sample proportion, just like we did with the population mean and sample mean. Now, this is kind of a requirement. I won't ever try to trick you with this, but just to be a little bit more thorough in here, we have to make sure that this, given whatever we think the population proportion is, we need the sample size to be large enough to get us over 5 here. Right? So the confidence interval equation for our sample proportions is going to be very similar to what it would be for our sample means. It's just now we're basing it off of the sample proportion instead of sample mean. We know we can still use that standard normal distribution to look up how many standard deviations away we want to go. And now what this represents, remember, is the standard deviation of my standard deviation of my sample proportions, right? I could just plug this in here. Right? That was how I was estimating it, right? So before we had the standard deviation of our sample means here, right? If we go back, really what was in here was the standard deviation of our sample means, which we could have just plugged this in there. Now we've got the standard deviation of our sample proportions, which we know we are estimating with this equation. Okay. So we've got our margin of error here. Like I said, it's more accurate to use it with proportions. I probably shouldn't technically be using it with sample means, but to keep it consistent, I think it makes it easier for you guys. All right, here's our margin of error. We're going to add and subtract that to the sample statistic we found. Now it's a sample proportion. Add it to get the upper bound, subtract to get the lower bound, and now we'll have a confidence interval for where the true population proportion is. Very similar process, right? So I've got a couple examples I'll kind of talk through here, and then I'll probably end this recording and do a separate one for what would be then Thursday's lecture. So a March 2012 poll about the Affordable Care Act, or Obamacare as it's known as, found 63 out of 81 people favored the requirement that insurance companies cover people with pre-existing conditions. Okay? So we've got 63 out of 81, and we want to know with 99% confidence, I want to create a 99% confidence interval that I could say that the true population proportion is within this lower and upper bound. And that might be important because when I'm trying to get this policy through, I want to know what proportion of the populace supports it. Okay? But all I have is this sample of 81. The country's a lot bigger. So, what do? Well, just as a reminder, right, because we've got these different benchmarks we're going to be interested in. We usually are just looking at 90, 95, 99. The z-values, oh, there's a typo here. This decimal should be moved over one. Right? The z-scores that we need are going to be right here. So 1.65 is what we'd find if we looked up for a 90% confidence interval. 1.96 if we wanted 95%, and 2.58 if we wanted 99%. Okay? So I'll kind of go back to those so I don't have to talk about what it would look like if you looked it up in the table every time. So what is another sample proportion in this example? If I go back here, I wasn't given it explicitly. But sample proportion is like this number out of how many people that was in our sample. So here, 63 out of 81, so 63 divided by 81 would be the sample proportion of people who were in favor of this. So 63 over 81 gives us, simplifies to 7/9 and gives us this 0.778. Our sample size was 81 people we sampled, and if we wanted to do this at the 99% level, I don't think I actually, did I explicitly say that here? Oh yeah, 99%, so the area outside that interval, 1%, decimal form, 0.01. That's how we'll think about it. So I looked that up in the table. I don't know why this is wrong. I'll have to update this value. This should not be 0.495. We should be looking at 0.005, right? Alpha over 2, 0.005. So I'll alter that and upload the complete version, or re-upload the complete version of the slides. So we looked that up. We'll find 2.58, right? And that was kind of from our benchmarks here. If I want the alpha of 0.01, the area within my confidence interval is 0.99, that'd be 2.58. Okay. I then do my intermediate calculation. I can find that standard deviation of my sample proportions with this estimate, right? And so I had 7/9 here. It was 63 out of 81, which simplified to that, and it was just like easier to kind of see. But all I'm doing is plugging those in. If I put 1 minus 7/9, I get 2/9. Plugging my sample size to calculate that standard deviation of my sample proportions. Now it's just a matter of plugging everything in. Right, so plugging my sample proportion of 0.778, plugging that z-score I needed of 2.58, and plugging that standard deviation of my sample proportions. Okay. Now notice here, I just wrote this as the standard deviation of my sample proportions. If I didn't want to do the intermediate step, I could just write it out this way and go ahead and plug everything in, right? So either way will get me the same answer. Alright, so this would have been an ninth grade question. Be a good one to know how to solve. If you're working through it, and you have any questions on solving this one, let me know. Okay? Send me an email. So this one, I had a much higher sample, 912 instead of 81. And I believe I took this from Fox News in the last election. I thought it was interesting. 46% of people said they were going to vote for Clinton. So I might want to try to predict the upcoming election, and I want to create a confidence interval where we can say, okay, what's the true proportion of people who are going to vote for Clinton? Well, I have 46% here, so that'd be a proportion of 0.46. That was the sample proportion I found. If I want to build a 90% confidence level, that would be an alpha of, well, 10% outside of the interval, in decimal form, 0.1. Right? And my sample size is 912. That's all I need. That's all I need, right? If I look at this sample proportion of 0.46, it looks like it's in the middle of all these. I don't think there's any we can rule out. So we'll just go ahead and plug things in. If we look at kind of our benchmark values and remember, okay, we wanted the 90% level, 90% confidence level, so 0.9, that will be a z-score of 1.65. Okay? So I have these three things I need. I can look up that z-score if I didn't have the benchmark table in front of me, right? So alpha is 0.1, divided by 2 is 0.05. I go to my z-table, look in the middle, go over. I find that that z-score is 1.65, right? Or negative 1.65, and then I just remember, yeah, I don't need the negative sign there. I can do the intermediate calculation of finding my standard deviation of my sample proportion, so I plug in that sample proportion of 0.46, plug in my sample size of 912, and I get that. Right? And then go to my confidence interval equation, now have everything I need, just plug it in, and I get my lower and upper bound. So, back in 2016, I could have said, with 90% confidence, right, that's what I was starting out with, 90% confidence, that the true proportion of people that would vote for Clinton in the upcoming election would be somewhere in between these two values. So I want to be able to do some predictions with political polling like this. Okay? I can do the same thing for Trump. And here I'm pretty sure I have a typo, so let me change this as I'm explaining it just so we don't get confused. is 5.2. Okay. So for Trump, we could do the exact same thing, but now we found that the same poll said only 40% of people were going to vote for him, so our sample portion is 0.4. We still had 912 people in the sample, so we go ahead, plug everything in, and we get, this is our lower and upper bound. Now why this is interesting, I like this example for political polling, is because if I think about this, right, if I know that the true population proportion with 90% confidence is somewhere in between this value for Trump, so at the very most, 42.67%, or the proportion of the population that will vote for him is 0.4267, that's the highest it could be with 90% confidence. But if I look at Clinton, we go back here, the lowest that the population parameter could be given our confidence interval is 0.4328. So even if we had the lowest value for Clinton and the highest possible value for Trump, Trump would have had a lower proportion of the votes, or at least that's what this poll would have predicted. Right? So that's what this poll would have predicted if these confidence intervals don't overlap. Right? If they don't overlap, right, then the highest proportion for Trump was less than the lowest proportion for Clinton. Now what if, sorry, I'm going to change these numbers just to kind of make a point. What if Clinton's would have been something like, I don't know, this? Well, now it could be that Clinton, the true population proportion of people who are going to vote for her was, let's say it was 0.419, right? That would be above this within our range. So let's say it ended up being 0.419. And here for Trump, it ended up being 0.424. Well, now, because the confidence intervals do overlap, yeah, the true proportion for Trump could be higher than what it was for Clinton. Right? So, we talked about this a little bit in the Excel file as well. If we have confidence intervals that overlap, we can't say which of those groups or which of those people is going to be higher. Right? But if they don't overlap, well, then we do know one of them with a certain level of confidence would be higher. Right? So, I believe that's going to end this first one. I'll try to get this uploaded and then film another one that would be more like Thursday's lecture. Thursday's lecture would have also included working through Excel, so I'll have that file up there as well. I already have that recorded. I know this isn't ideal. I wish I could have had a little bit more of a kind of video associated with this. I will likely be doing a little bit more video moving forward. I'm going to have a whiteboard that I can do some of the stuff that I can't do in PowerPoint here, if I can't point to certain things or give you a nice visual. But if you have any questions, I'm actually not going to be hosting any office hours given the current climate. So if you do want to talk to me, I can always video with you. I have hopefully I don't call the wrong thing, WebEx. We could set up a time to kind of, I have a webcam so we could talk to you that way. If you ever wanted to call me, I'll actually, I don't know, this might not be a good idea, but I'm putting my number up on Canvas as well, so that you can call if you want to just do audio. And then also, I'm going to be available via email all the time. I'm going to be working every day. Honestly, it's taking me more time to create these videos and voiceovers than it would be to teach the class, and so I'll always be working. Please feel free, excuse me, to reach out. That was because I've been talking a lot, not because of the virus. But so reach out with questions. I'll try to answer them at the beginning of next week's film lectures. I'm going to try to kind of get a little bit ahead on these, but I think I can video splice things in like at the beginning to address any questions that you might have. Okay.